Today, we are cracking open one of the deepest and honestly strangest secrets in all of physics. It's this property of matter that's so fundamental that without it, well, you, me, and the entire universe just wouldn't be here. We're talking about quantum spin. So let's start at the beginning. Where did this incredibly weird idea even come from? Our story kicks off way back in 1922 with what sounds like a pretty simple question. Let's say you take a beam of atoms, just regular neutral atoms, and you fire them through a specially designed magnet. This magnet doesn't have a nice uniform field. It's stronger on one side than the other. So what do you think you'd see on a detector screen placed on the other side? All right, so here's the actual setup for the experiment, which is now famously known as the Stern-Gerlach experiment. First, you've got a little oven, and it's cooking up silver until a fine spray of individual neutral atoms comes out. That beam then flies right through this special magnet. And finally, the atoms hit a detector plate, and they leave a tiny mark where they land. Seems pretty straightforward, right? And this is where reality just completely departed from the script. According to all the physics they knew at the time, classical physics, these little atoms are like tiny compass needles. Since they're flying out of the oven all jumbled up and pointing in random directions, you'd expect the magnet to push them all by different amounts. The result? It should have been a single continuous smear on the detector screen. But that is not what they saw. Not even close. What they got was two distinct separate spots. Just two, with a big empty gap right in the middle. I mean, this result was a complete bombshell. It was impossible. There was just no way, according to the rulebook of physics, for a random spray of tiny magnets to neatly split into two perfect beams. This was the first undeniable proof that there was something hiding inside these atoms, some secret property that nobody had ever imagined. And whatever this property was, it wasn't continuous. It was quantized, meaning it could only take on specific, distinct values. So what was this secret property? Well, physicists eventually gave it a name, spin. But I promise you, what that name actually means is a whole lot stranger than you might think. Okay, so here's the textbook definition. Spin is an intrinsic angular momentum. Let's break that down. When we say intrinsic, we mean it's a fundamental part of what a particle is, not what it does. You know how an electron has a charge and it has a mass? You can't take those away. They're part of its identity. Well, spin is exactly the same. It's just built in. And, this is key, it is a purely quantum thing. There's really nothing like it in our everyday world. This really gets to the heart of the problem. You hear the word spin, and you immediately picture a tiny little ball rotating on its axis, right? Totally understandable, but also totally wrong. As far as we can tell, an electron is a single point. It doesn't have a surface. It can't literally be spinning. So those quotation marks around the word spins are there for a very good reason. They're a warning that we're using a familiar word as a label for something that is deeply, deeply unfamiliar. And if you thought that was weird, just wait. The mystery goes to another level when we look at the actual value of an electron spin. It's not a whole number. It's something that honestly feels like it shouldn't even be possible. Yep, 1/2. The spin of an electron is 1/2. Every single electron in the entire universe has this exact same, unchangeable amount of spin. It's not just a random number, it's a fundamental constant of nature. But what on earth does it mean for something to have a spin of 1/2? So what that 1/2 actually means connects right back to those two spots in our experiment. It means that whenever you try to measure an electron's spin, no matter which direction you measure it from, you will only ever get one of two possible answers. It's either aligned with your measurement, which we call spin up, or it's perfectly anti-aligned, which we call spin down. That's it. It's a binary choice. And suddenly, those two spots make perfect sense. They were just the atoms with spin up electrons and the atoms with spin down electrons. Okay, so spin is this weird two-state quantized property. But why does it matter so much? Why should you care? Well, it turns out this little quantum quark is responsible for the single most important rule that governs the structure of, well, everything. That spin of 1/2 leads directly to something called the Pauli exclusion principle. Here's the simple version. You cannot have two identical particles of matter, like two electrons, in the exact same quantum state at the exact same time. These particles with half-integer spin get a special family name. They're called fermions. And for fermions, it's like there's a fundamental no vacancy sign hardwired into the universe.
Now, to really understand how massive this rule is, let's just do a quick thought experiment. Let's pretend for a second that this principle just didn't exist. What would a universe without it even look like?
Well, it would be a mess. Without this exclusion rule, there would be nothing to stop all the electrons in an atom from just dogpiling into the most desirable spot, the lowest energy level, right down by the nucleus. They'd all just collapse into one big, dense, mushy blob.
And what does that mean? It means atoms couldn't have structure. The beautiful shells and orbitals that make up the periodic table, gone. The entire field of chemistry wouldn't exist. This exclusion principle is what forces electrons to stack up neatly in different energy levels, and that is what allows for chemical bonds and the rich, complex universe we see. So that weird little spin 1/2 value, it's not just a curiosity, it is the architect of reality.
So, we've seen how spin builds atoms, which is pretty incredible, but its importance is actually even bigger than that. It acts like the universe's ultimate sorting hat, dividing every single particle that exists into one of two giant cosmic families. That's right. This isn't just about electrons. Every fundamental particle, from quarks to photons, has its own intrinsic spin. And the value of that spin, whether it's a half integer or a whole integer, determines everything about which family it belongs to and how it behaves when it gets together with its friends. And here are the two families. On one side, you've got the fermions. These guys have half-integer spin, like our electron with spin 1/2. They are the building blocks of matter. And they are the antisocial loners of the universe. They have to obey the Pauli exclusion principle. On the other side, you've got the bosons. They have integer spin, 0, 1, 2, and so on. They're the particles that carry the forces, like photons, which carry light. And unlike fermions, bosons are total party animals. They love nothing more than to all pile into the exact same state. In fact, that's exactly what a laser is, just a whole bunch of photons having a party in the same quantum state. Now, this incredibly deep connection, this idea that a particle's intrinsic spin dictates its social behavior, is formalized in something called the spin statistics theorem. It's not just a neat pattern, it's a cornerstone of modern physics. And yet, and this is the part that just blows my mind, for all of its importance, this connection is still profoundly mysterious. The great physicist Richard Feynman once said that it's a rule you can state very simply, but one for which nobody has ever found a simple and easy explanation. We can prove it with very advanced math, sure, but no one can give you a gut-level intuitive reason why half-integer spin means keep your distance and integer spin means everyone pile in. It's just one of the fundamental, strange secrets of our universe, a secret that makes everything else possible.